Hello my friends and welcome back to the You Can Do TV channel. The transformation of raw ore into steel involves a series of intricate steps, each critical to achieving the desired quality and specifications. Raw material preparation. The process begins with the procurement of iron ore, scrap steel, and other raw materials. These are meticulously prepared and sorted to ensure high-quality inputs for the subsequent stages. Melting in electric arc furnaces, EAF, at Kardemir's Izmir facility, the state-of-the-art Fescon electric arc furnace, with a capacity of 100 tons, melts the prepared materials. Advanced technologies like waste heat recovery reduce energy consumption by 15 to 30%, aligning with sustainable manufacturing practices. The melted material is then refined to eliminate impurities and adjust chemical compositions. Billet casting. The molten steel is cast into billets, a semi-finished product, in the steel mill. These billets serve as the primary feedstock for rolling mills and other downstream processes. Kardemir's steel mill boasts a production capacity of 1.2 million tons annually, meeting the demands of various industries. Rolling and shaping. The billets are reheated and processed in rolling mills to produce a variety of steel products. Kardemir operates 4 rolling mills for this purpose. The Denizli Profil Factory and Izmir Aliaga Profile factories collectively produce 700,000 tons of structural profiles annually, while the wire rod and rebar production facility, operational since 2023, produces 600,000 tons annually. This facility features one of Turkey's longest cooling lines and fully automated production systems. Kardemir Çelik Sanayi A.S., a leading steel manufacturer established by Nevzat Karal and his family, exemplifies excellence in this production process. With facilities in Denizli and Izmir, Kardemir has continuously expanded its operations, producing a diverse range of steel products for both domestic and international markets. Advanced finishing and packaging. The steel products are subjected to finishing processes like cutting, shaping, and surface treatments to meet specific customer requirements. Automated systems ensure precision in packaging and dispatch. Distribution and export. With over 50% of its production exported to 110 countries, Kardemir is a key player in the global steel market. In 2023, exports approached $225 million, reinforcing its position among Turkey's top industrial exporters. The Beloretska Spring and Leaf Spring plant stands as one of the largest manufacturers and suppliers of springs and leaf spring products in Russia and nearby countries. With over 7 decades of experience, the plant has undergone significant transformations, focusing heavily on technological advancements in production processes. The primary production processes at Beloretska plant are centered around 2 main types of spring manufacturing: cold winding and hot winding. Cold wound springs are produced using steel wire that is formed at room temperature, ensuring high tensile strength and durability. This method is typically employed for smaller springs used in precision applications. In contrast, hot wound springs involve heating steel rods to a specific temperature before winding them into shape. This process is used to produce larger, heavy-duty springs for automotive and industrial use, offering superior load-bearing capacity. Heat treatment plays a crucial role in enhancing the mechanical properties of the springs. Advanced thermal processing technologies, such as induction heating and electric conveyor furnaces, are used to achieve the desired hardness and flexibility of the springs. Over time, all heating systems were converted to operate using natural gas, improving both energy efficiency and environmental sustainability. In the late 20th century, the plant expanded its production range by introducing leaf springs for tractors and heavy vehicles. The manufacturing of leaf springs involves cutting, forming, and heat-treating metal strips, followed by precision assembly to ensure proper load distribution and durability. The plant also implemented automated testing systems to ensure the springs meet stringent performance and safety standards. By the 1990s, the plant specialized in producing over 600 types of springs, focusing on both standard and custom products. Continuous upgrades in metal cutting machinery and grinding equipment further enhanced production capabilities. In addition, new lines for parabolic springs, known for their reduced weight and increased load capacity, were introduced. The necessary equipment for manufacturing parabolic springs was procured from leading international suppliers, underscoring the plant's commitment to adopting advanced technology. Today, the Beloretska plant operates with a monthly production capacity exceeding 4,000 tons, including 35 tons of cold wound springs and 500 tons of leaf springs. The company maintains a rigorous quality management system certified to international standards, ensuring consistent product performance and reliability. Additionally, the plant actively develops new products to meet the evolving demands of the domestic and global markets. The integration of modern machinery, automated lines, and advanced heat treatment technologies has established the Beloretska spring and leaf spring plant as a key player in the mechanical engineering industry. With a focus on innovation, quality, and market expansion, the plant continues to contribute significantly to various sectors, including automotive, agriculture, and industrial machinery production. The Dayco spring grinding machine is designed for precise grinding of coil springs. The machine consists of a grinding unit equipped with a control panel for easy operation. It grinds both ends of coil springs to achieve accurate parallelism and ensure consistent spring height. An optional supplying tower unit can continuously feed springs into the machine for high-volume production. Additionally, optional automatic loading and unloading devices enhance efficiency by minimizing manual handling. The machine's precision grinding capabilities improve surface finish and dimensional accuracy, making it ideal for manufacturing springs used in critical applications like automotive, aerospace, and industrial machinery. The leaf spring production industry is critical for automotive and heavy vehicle suspension systems, ensuring load-bearing capacity and stability. Typically made from high carbon or alloy steel, leaf springs undergo processes such as cutting, heat treatment, shot peening, and cambering. The industry uses SAE 5160 or 50 CRV4 steel grades, achieving tensile strengths of 1,300 to 1,600 megapascals. Production capacities vary, with large plants capable of producing over 50,000 tons annually, supplying OEMs and aftermarket segments. Advanced heat treatment lines operate at 900 degrees Celsius to 950 degrees Celsius, with precision-controlled quenching and tempering for enhanced durability. Automated cambering machines ensure a tolerance of plus or minus 0.5 millimeters. The use of robotic shot peening improves fatigue life by 20% to 30%, ensuring compliance with strict industry standards like ISO 9001. The production facility of Armoson hot-rolled seamless pipe industry, located in Edirne's organized industrial zone, spans 15,000 square meters of open area and 8,000 square meters of covered space. The production process begins with the selection of high-quality alloy steel that meets international standards. Each batch of raw material undergoes rigorous quality testing before processing. Steel billets are heated to the required temperature and shaped without any material removal. Drilling is performed on the heated billets to create a hollow section, forming the initial seamless pipe. In the first and second pipe drawing units, controlled cooling and reheating cycles are applied to preserve the material's molecular structure and physical properties while ensuring dimensional accuracy. Following these processes, additional treatments such as external threading of the pipes are carried out. The plant specializes in the manufacture of hot-rolled seamless steel pipes with wall thicknesses ranging from 5 mm to 15 mm and self-drilling anchor bolts, a specific form of seamless pipe designed for anchoring applications. For self-drilling anchor bolts, production involves advanced hot processing techniques. These bolts are designed for use in unstable ground conditions, such as hard and fractured rock formations, loose soil, or mixed ground. The bolts are essential in tunneling, mining, and slope stabilization applications, offering a reliable solution for anchoring and load transfer. Accessories required for the installation of these bolts, such as couplers and drill bits, are also manufactured in-house. The facility currently produces approximately 150,000 meters of self-drilling bolts per month, with plans to double this capacity within 2 years. This wire drawing line is a continuous production system used to reduce the diameter of metal wire by pulling it through a series of progressively smaller dies. The process begins with feeding large diameter wire into a payoff reel, which guides it into the first die. As the wire passes through each die, it undergoes plastic deformation, reducing its diameter while increasing its length. Lubrication is applied to minimize friction and heat buildup. Between each die, capstan or drawing drums maintain proper tension and speed. After drawing, the wire is coiled onto a take-up reel for further processing or packaging. Stainless steel tubes are produced through a technologically advanced process to ensure high-quality output. The manufacturing begins with the selection of premium-grade stainless steel coils that comply with global standards like ASTM and N. These coils are cut into strips of desired widths using precision slitting machines. The strips are then passed through advanced tube mills, where they are formed into round, square, or rectangular shapes using a series of rolls. During this process, the edges of the strip are brought together and welded using high-frequency or TIG, tungsten inert gas, welding technology, depending on the tube's specifications. The welding process ensures a seamless bond and a consistent finish. After welding, the tubes undergo deburring to remove any weld spatter or irregularities. The weld seam is further planished to create a smooth surface, enhancing the aesthetic and structural quality of the tube. The tubes are subjected to solution annealing, a heat treatment process that eliminates internal stresses and improves corrosion resistance. Post-annealing, the tubes are pickled and passivated. This chemical process removes scale, impurities, and contaminants, forming a protective oxide layer that enhances the stainless steel's corrosion resistance. The tubes are then passed through polishing units to achieve the desired surface finish, ranging from 180 to a high-gloss mirror finish like 600. These finishes are achieved using abrasive belts and polishing compounds. Precision cutting machines trim the tubes to the required lengths, ensuring dimensional accuracy. Following this, stringent quality control measures are applied. Non-destructive testing methods, such as eddy current testing or ultrasonic testing, verify the integrity of the weld and overall structure. Dimensional checks and surface inspections ensure compliance with specified tolerances. Composite Machine Tools specializes in producing advanced machining centers for industries such as aerospace, defense, automotive, and energy. The production process integrates the expertise of two renowned brands, Ingots and Ingots, resulting in high-performance, innovative solutions. The company employs state-of-the-art technologies, including automated systems and fiber placement heads for composite materials, ensuring precision and adaptability for special applications. Each machining center undergoes rigorous testing before delivery, ensuring reliability and efficiency. Additionally, the company provides tailored solutions, from strategic process evaluation to machine installation, enhancing customer productivity. By leveraging advanced technological platforms and reducing system development times, the company positions itself as a key partner for industries seeking high-quality machine tools and long-term support. Copper tube manufacturing begins with the selection of high-quality copper cathodes, which are melted in a furnace at controlled temperatures. The molten copper is then cast into billets, which undergo hot extrusion to form tubes with the desired diameters and thicknesses. These tubes are further processed through cold drawing to achieve the required precision in wall thickness, diameter, and surface finish. The next step involves annealing, where the tubes are heated and cooled to improve flexibility and mechanical properties. For products like inner groove tubes, special grooves are formed inside the tubes during the drying process to enhance heat transfer efficiency. Pancake coils and straight ACR tubes are produced by cutting and coiling the tubes to specified lengths and shapes. Each stage of production is closely monitored by quality inspectors, ensuring compliance with international standards. Non-destructive tests, including eddy current detection, are conducted to detect defects. The finished tubes are carefully packaged and labeled to prevent damage during transportation. The copper rod upward continuous casting machine is designed for the efficient production of high-purity copper rods directly from copper cathode or bright copper scrap. The process integrates melting, casting, and wire drawing into a seamless operation. Melting furnace. Copper cathodes or bright copper scrap are fed into the melting furnace, where they are heated to a liquid state. The molten copper is maintained at a controlled temperature to ensure uniformity and purity. Freezing and upward drawing. The molten copper flows into a crystallizer, where it is rapidly cooled and solidified. This upward continuous casting technique ensures minimal oxidation and high-quality output. The solidified copper is drawn upward, forming rods with a diameter of approximately 20 millimeters. Tension frame and wire separation device. The rods pass through a tension frame to maintain consistent pulling force, ensuring uniformity. A wire separation device is employed for further refinement. Take-up machine. The continuous copper rod is wound onto take-up reels, facilitating efficient handling and storage. Wire drawing plant. The rods are transferred to a wire drawing machine, where they are processed into thinner copper wires, typically 8 mm, 3 mm, or 2.6 mm in diameter. The wire drawing process involves successive reduction stages to achieve the desired thickness. This streamlined operation, controlled by advanced electric control cabinets, enables precise production with minimal waste, supporting industries like electronics, construction, and automotive manufacturing. The continuous casting and rolling (CCR) plant for copper rod production is an advanced facility designed to efficiently produce high-quality copper rods for various applications. The process begins with molten copper being cast into billets, which are then continuously rolled to the desired diameter. The CCR plant uses high-speed rolling mills to shape the copper into rods, followed by cooling and annealing to enhance the material's properties, such as electrical conductivity and ductility. The plant is equipped with advanced control systems to ensure precise temperature and speed control throughout the process. The final copper rods are wound into coils for ease of handling and shipment, serving industries like electrical wiring, construction, and electronics.
Steel fabrication comes alive inside a vast workshop in Johor Bahru, Malaysia, where raw H-beams begin their journey. Here, CNC automatic drilling machines with 3-axis capability tackle each beam with impressive speed, boring precise holes according to custom designs. Next, CNC cutting machines swiftly shape the steel to exact lengths, while CNC punching machines create connection points for later assembly. After cutting and punching, skilled operators perform fit-up, aligning each piece and preparing for welding. Powerful welding equipment then bonds the sections together, forming robust steel structures ready for heavy-duty use. Once the frames are assembled, the surfaces undergo manual shot blasting to remove scale and ensure optimal paint adhesion. The fabrication continues with a primer coat, followed by a second layer and finally a finishing coat of paint. Each phase is closely monitored to meet strict quality standards, resulting in beams ready for large-scale construction projects. Watching these machines and workers in action is truly impressive. It's a reminder of how much expertise and coordination go into every finished structure. Watch as massive steel parts are shaped on the Lagun moving column milling machine. The heavy workpiece is locked onto the table, while the machine's column glides along powerful rails. Precision tools carve complex features, from deep pockets to smooth surfaces, all controlled by advanced CNC systems. Each pass of the cutter is calculated and steady. Seeing these machines handle such scale and detail, you really appreciate the engineering and technology behind modern manufacturing. Inside the forging hall, a massive hydraulic press dominates the scene, using hydraulic pressure to shape glowing steel into shafts, blocks, and discs. The operator carefully maneuvers each hot billet under the press, and with a thunderous stroke, the metal transforms into precise forms. Open die forging like this allows for the production of custom shapes. Each step requires both power and skill. Watching the red-hot steel get molded under intense pressure is genuinely thrilling. The result is tough, reliable parts ready for heavy-duty applications. Longwall mining is a highly automated method for extracting coal deep underground. Powerful shearers slice coal from the face, while hydraulic roof supports keep the ceiling stable, advancing in sync as the seam is mined. Crushed coal falls onto massive conveyor systems, traveling through tunnels to the surface for processing. Every component, line pans, stage loaders, and drive frames, works together for continuous production. Watching this operation, you realize just how much engineering is behind modern mining. The precision, scale, and teamwork on display make longwall mining a core process in keeping the world's energy supply running strong. Creating a Torino alloy rim wire wheel starts with precision and raw material. A thick-walled aluminum tube is cut to length, then squared and smoothed on the lathe. Next, a 200-ton press shapes both ends using custom plugs, preparing the tube for spinning. The blank is mounted on a CNC spinning machine, heated and gradually formed by rollers until it takes on the rim's final profile. After spinning, the rim is lathed again to fine-tune the thickness and interior shape. Polishing follows, starting with coarse sanding, moving down to finer grits, then to polishing mops for a mirror finish. Now comes marking and preparing the wheel. The rim is carefully marked according to the spoke pattern. Each mark is used to press a dimple, forming a seat for the spoke nipple. Next, holes are drilled at precise angles for each spoke row, top, middle, and bottom, with a special tool to ensure exact spacing. Stainless steel spokes are bent, cut, and threaded with a rolling machine. Assembly is done row by row with constant checks on offset and tension. Truing ensures the rim runs perfectly straight, within 0.5 millimeters. The builder stamps their mark inside the rim before packing for delivery. Every step reflects real dedication. Inside the factory, the MSM 320B mesh welding machine goes to work, welding wire intersections to form reinforcement mesh for box culverts and concrete pipes. Each wire is automatically fed and positioned, then welded with impressive speed and accuracy. The mesh produced is crucial for flat elements, L-Mias, and U-shaped concrete parts. Watching the machine operate, you can't help but appreciate how each weld point contributes to the strength of these massive structures. This level of automation is genuinely fascinating. Steel rods roar as massive presses shape them into durable components. Workers handle red-hot metal with swift, practiced moves, each forging step boosting strength and quality. The factory's controlled chaos feels intense. Watching raw steel transformed under such force is truly impressive. Plutonium production at Hanford powered a critical chapter in U.S. history. Inside the finishing plant, workers handled radioactive material with immense caution, preparing metal for weapons. Now, every step in decontamination demands strict safety, an intense, high-stakes effort to contain risk. The legacy here is both daunting and unforgettable. Inside the Severstal Dearborn mill, steel production begins with red-hot slabs moving through powerful rolling mills. Massive rollers reduce each slab's thickness, shaping the steel for automotive and construction uses. The line continues with precise cooling and straightening processes, ensuring each sheet meets strict quality standards. Automated systems and skilled workers monitor every stage, making adjustments in real time. Watching the transformation from glowing slabs to flawless steel sheets is truly impressive. This is industrial power and precision in action, right before your eyes. The new rolling mill marks a fresh era for heavy plate production. With a rigid stand and precise adjustment systems, it achieves a massive 8,000-ton rolling force and 2 by 7,500 kN torque. Watching thick steel plates shaped so effortlessly is fascinating. Every pass improves thickness, accuracy, and flatness. The whole process looks incredibly powerful. This level of engineering really grabs your attention. The VB400M confidently mills out cylinder holes with unmatched precision. Every rotation guarantees a flawless finish. Watching this machine work, there's no doubt this is real industrial excellence in action. Watching a massive steel block measuring 1,000 by 1,000 by 1,200 millimeters and weighing nearly 7 tons, take shape is nothing short of impressive. The process begins with open die forging, where intense heat and force create a solid, homogeneous block. After cooling, preparations start for the oxy-fuel flame cutting stage. Workers use an oxygen lance to pierce a hole, followed by flame cutting of 500 millimeters diameter, opening through 1,200 millimeters of solid steel. Precision matters at every second. Cutting the outline requires steady hands and focus, especially with such tough material. A deep cone, 600 millimeters in depth, is also flame cut into the block, demonstrating the sheer capability of this technology. Next, the piece is sent to the lab for rigorous testing, including Charpy impact and tensile strength tests, ensuring quality and durability. After milling the final contour, the finished product is carefully packaged. Seeing each stage up close, you can't help but appreciate the skill and technical power behind these operations. Steel plates are pressed and formed into cylinder shapes, then welded to ASME standards. CNC profiling ensures perfect cuts. Watching these steps, you can really appreciate the skill behind every cylinder. Aluminum production begins at open cast mines, where bauxite ore is extracted just beneath the surface. The ore is crushed, ground, and mixed with hot caustic soda to form a slurry, then heated to 270 degrees Celsius in the digestion stage. After impurities settle in clarification, alumina crystals are formed by cooling and precipitation, then heated to 1,100 degrees Celsius in calcination, creating a fine white powder. Next, alumina enters reduction cells lined with carbon electrodes, where electric current at 400 kA separates pure aluminum at about 960 degrees Celsius. Liquid aluminum is then poured into molds, solidifying into ingots or sheets. The whole process is an impressive display of industrial precision and high temperatures. Seeing metal flow like liquid is fascinating every single time. Few machines command attention like this extra heavy-duty lathe. Handling jobs up to 45 metric tons, with a center height of 60 inches and a massive 30-foot bed, it's built for pure muscle. Watching technicians load and secure enormous workpieces, then seeing the lathe-shaped steel with such power and precision is incredible. Each rotation transforms raw metal, and the scale of this process is genuinely jaw-dropping for anyone who loves engineering. Witness the power of metal forming as a massive steel plate is rolled into a cone with a diameter of 4.5 meters. The rolling machine applies intense force, steadily shaping the plate into a precise, conical form. Operators monitor every step, ensuring even curvature and a perfect fit for heavy-duty applications. Each pass of the rollers transforms the plate further, and the scale of this process is truly impressive. It's a great example of skill and strength coming together in industrial fabrication. The 4-roll plate rolling machine bends and rolls thick steel plates into large cylinders in one smooth, continuous motion. High plate pinching power and precise edge alignment minimize re-rolling and speed up production. Watching thick steel plates shaped with such efficiency and accuracy is impressive. The automation system barely needs an operator. Every stage, from feeding to tack welding, is tightly controlled for smooth, rapid results. The EVERISINGE 530 high-tech bandsaw is a precision cutting machine designed for heavy-duty industrial applications. In this case, it's demonstrated cutting SKD61 tool steel, a high-alloy, hot-work die steel known for its hardness, toughness, and excellent heat resistance. With a diameter of 404 millimeters, the SKD61 billet demands both cutting power and accuracy, which the E530 delivers effortlessly. The machine begins with the clamping system securing the round billet firmly in place to prevent vibration or movement during the cutting process. This is crucial when dealing with dense tool steel, ensuring a straight and clean cut. The E530 is equipped with a robust hydraulic feed system that applies consistent downward force, optimizing blade pressure and cutting speed. The bimetal or carbide-tipped bandsaw blade runs through a set of guided rollers and maintains high tension, which reduces blade deflection. The coolant system engages simultaneously, directing coolant precisely at the cutting zone to reduce heat buildup, prolong blade life, and maintain material integrity. Thanks to its programmable logic control, PLC, the E-530 allows operators to preset feed rate, cutting speed, and return stroke, ensuring repeatability and reducing cycle time. The machine completes the cut in minutes, leaving a smooth perpendicular surface with minimal burring. This operation demonstrates the E530's capability to process tough alloys with high efficiency, making it ideal for mold shops, tool makers, and steel distributors requiring consistent, high-volume cutting of hardened materials. The aluminum foil rolling mill precisely reduces aluminum ingots into ultra-thin foil through multiple passes. Using high-tension rollers, automatic thickness controls, and coolant systems, it ensures uniformity and surface finish. Final gauges can reach microns, ideal for packaging, insulation, and electronic applications. Composite fan blade production begins with laying carbon fiber sheets into a mold, followed by resin infusion and curing in an autoclave. After hardening, the blades are trimmed, machined, and inspected for precision. This process produces lightweight, durable blades that enhance engine efficiency and reduce fuel consumption in modern turbofan aircraft. The ARGS Vive Z950E is a stationary high-performance shredder designed for heavy-duty metal processing. In this setup, it is shown shredding car bodies with ease. The machine is powered by two powerful electric motors, each delivering 250 kilowatts of energy, ensuring consistent and efficient shredding performance. Its robust twin-shaft system handles bulky and complex scrap materials such as vehicle shells with high throughput. Built for continuous industrial operation, the VZ950E offers low maintenance, reliable operation, and high torque output, making it ideal for metal recycling facilities that require robust performance and energy-efficient operation in demanding environments. The V process, or vacuum molding process, is an advanced sand casting method used to produce high-precision components like axles. The process begins by heating a thermoplastic film and applying it over a heated pattern. This film adheres tightly to the pattern surface, forming a smooth, non-stick barrier that ensures excellent surface finish on the final casting. A joint riser and pouring cup are positioned, and the mold is sprayed with a refractory coating to enhance thermal resistance and prevent sand erosion. After coating, the flask returns to the molding station, where vacuum is applied to secure the film. Dry, unbonded sand is added to the flask and compacted under vacuum, which holds the sand rigidly in place without chemical binders. A manipulator then lifts and inverts the mold to expose the cavity. The core setting station inserts pre-made sand cores for internal features, and the two mold halves are assembled precisely. Molten iron is prepared and transferred into the pouring station. The iron is poured smoothly into the cavity through the riser and cup system, ensuring even filling and minimal turbulence. After cooling and solidification, the vacuum is released, and the mold collapses easily, allowing the casting to be removed without damage. The V process offers high-dimensional accuracy, superior surface finish, and reduced post-processing. It also minimizes gas defects and allows for easy recovery and reuse of sand, making it both efficient and environmentally friendly, ideal for producing high-strength axle castings. The Bauxite adjustable wrench manufacturing process begins with cutting using 1,000 to 1,600 tons of force. The blanks are then forged and hot trimmed at 1,150 degrees Celsius, ensuring strength and durability. Shot blasting cleans the surface before punching and coining shape the adjusting mechanism. Induction heating to 860 degrees Celsius is applied for hardening and tempering. After polishing for comfort, a surface treatment, either chrome plating or phosphating, is applied. Assembly includes fitting the moving jaw and adjusting knurl. Tip polishing and laser marking follow. The handle is assembled using a thermoplastic elastomer for grip, and each wrench undergoes 100% performance testing for quality assurance. The Bandsaw Turnout's replacement project involves the precise removal and installation of railway turnouts to ensure safe and efficient track switching. Technicians begin by lifting existing turnouts using hydraulic rail jacks and cutting rails with abrasive saws. Pre-assembled turnout sections are then delivered and carefully aligned. Ballast is compacted, and thermite welding is used to join rail ends. Final steps include tamping, track geometry verification, and signal integration to restore full operational capacity. The Kobelco SK3500D is a super-large building demolition machine designed for high-rise structures. With a maximum reach of over 65 meters, it uses interchangeable front attachments for precision dismantling. Its robust base and hydraulic stability system allows safe operation at extreme heights, making it ideal for urban demolition projects with tight safety margins. At Lange & Sondermann, the blasting and shot peening of railway springs is a precision-driven process designed to improve durability and fatigue resistance. After heat treatment, parabolic springs are cleaned and tensioned with 20 tons of press force before entering the AGTOS blasting chamber. High-performance turbines project steel shot to compress and harden the surface, particularly on tension areas. A roller conveyor system ensures controlled feed rates, while protective enclosures minimize noise and media escape. Coil springs are treated in a second unit, using rotating shafts and lifting beams to achieve uniform peening. Shot media is continuously filtered and recycled. This process guarantees high surface quality, extending the service life of springs used in heavy-duty rail applications across global networks. Zappella Mechanica Zella specializes in precision machining of medium to large parts. Their CNC boring machines can handle diameters up to 1,250 millimeters and depths of 2,200 millimeters. Turning capacity reaches 1,680 millimeters and 6 meters in length. Using CAD CAM systems, the company ensures tight tolerances. Quality control includes ultrasonic and magnetic particle testing, supporting industries such as energy, petrochemical, and steel manufacturing. An overview of the Metro Tunnel. The Metro Tunnel is one of Australia's largest public transport infrastructure projects designed to transform Melbourne's rail network. It involves the construction of twin 9-kilometer rail tunnels beneath the city, connecting the Sunbury and Cranbourne/Pakenham lines. The project includes 5 new underground stations: Arden, Parkville, State Library, Town Hall, and Anzac, built using advanced tunnel boring machines, TBMs, and roadheader excavation in tight urban environments. Key components of the tunnel system include tunnel lining segments, station box excavation, waterproofing, and complex ventilation systems. The use of precast concrete segments ensures precision and durability under high-pressure geological conditions. Critical systems such as track slab construction, electrical cabling, signaling, and platform screen doors are integrated to support high-capacity trains. Once complete, the Metro Tunnel will remove major bottlenecks in the existing rail system, increase capacity by hundreds of thousands of passengers each week, and improve reliability across the network. Pipeline construction through rough terrain is no easy feat. It's a battle against nature, executed with machine precision. First, the right-of-way is cleared of trees, groomed, and blasted to level the ground. Then, massive pipes are delivered directly to the prepared path. Each pipe end must be beveled for automated welding. That's where the pipe-facing machine comes in, smoothing and shaping each edge for a perfect fit. Welding begins with alignment, followed by root and hot pass deposits. The process demands exact timing and coordination from every team involved. Multiple passes fill out the bevel completely. Every weld undergoes ultrasonic testing to ensure integrity. Once verified, the joint is sandblasted and coated to protect against corrosion. Then comes the final step, lowering the pipeline into the trench and backfilling the soil. It's raw terrain, relentless workflow, and relentless standards. Technoi's ice cream production lines start with precision mixing, where ingredients are blended to exact recipes. Rich ice cream mixture flows into molds with swirling precision, building perfect layers and patterns. Conveyor belts move each cup and bar smoothly down the line. Automated dispensers add vibrant sauces and crunchy toppings, transforming each product into a visual treat. The pace is incredible, so many varieties crafted in moments. Creating textile webbing slings begins with strong synthetic fibers woven tightly on automated looms. Each sling is stitched, heat-sealed, and tested for strength. It's impressive to see such reliability built in. A thick tube of heated plastic hangs suspended as the massive yellow molds slide into position. Hydraulic clamps close with a heavy snap, trapping the parison inside. Compressed air inflates the tube, forcing it to expand against every contour of the mold. You can almost feel the anticipation as the tank quickly takes shape. Once the cooling phase finishes, the molds open to reveal a fully formed water tank, still warm and perfectly shaped. The transformation is fast, powerful, and always satisfying to witness. Rotomolding IBC water tanks is a powerful display of modern manufacturing. The process begins with raw polyethylene powder loaded into a steel mold, which is then rotated and heated inside the massive machine. As the mold spins, the plastic melts and coats the inner surface evenly, forming the tank's durable walls. It's amazing to watch each cycle transform raw material into a seamless container ready for heavy-duty use. Technicians monitor the entire process, making real-time adjustments to guarantee perfect thickness and a flawless finish every time. Creating precision bobbins with the Starlinger twin tape winder is pure engineering satisfaction. Plastic tape winds perfectly onto each core, forming neat, even layers. The accuracy and speed here make reliable woven sack production possible. Ever wondered how a tiny matchstick is born from a tree and ends up lighting candles, stoves, and memories around the world? At Asia Matches, the journey from raw wood to a perfectly crafted matchbox is a precise, fascinating process driven by machines, chemistry, and craftsmanship. The production process of machine-made matchboxes at Asia Matches is a well-organized and highly technical sequence designed for efficiency and safety. It begins with peeling and chopping, where high-quality softwood logs are peeled and chopped into uniform match splints. These splints are then subjected to cleaning and sieving, ensuring any dust, bark, or irregular particles are removed. Next is the splints treatment phase, which involves carbonizing the cleaned splints. This process involves heating the wood to create a charred surface that slows down combustion and improves safety. Meanwhile, the printing process prepares the outer sleeves with branding and safety instructions using high-speed offset or flexographic machines. After printing, lamination is applied to protect the printed surfaces from moisture and wear. Then comes the friction application, where a special friction strip, made of powdered glass and binders, is applied to the side of the outer box to allow match ignition. The quality of each stage is verified in the lab, where random samples are tested for ignition quality, safety, and consistency. Production continues with outer box making, where printed and laminated board is folded and glued into sleeves. Simultaneously, inner box making shapes the sliding trays that will hold the matchsticks. All components are then assembled, filled, and packaged, resulting in a high-quality, reliable matchbox ready for distribution. The tissue mill has a production capacity of 140,000 tons and utilizes advanced Viscosoft technology, the first of its kind in Turkey. Using 100% virgin wood pulp, 2 high-speed paper machines form the base tissue rolls. These large parent rolls are then transferred to 12 consumer and 4 away-from-home converting machines, offering a total converting capacity of 120,000 tons. The process includes slitting, embossing, folding, and rewinding to produce various tissue products such as toilet paper, facial tissues, napkins, and hand towels, all with different textures, sizes, and ply specifications. The casting process for aluminum alloy wheels using a permanent mold involves precise temperature control and mold preparation. First, a steel mold is preheated and coated to prevent adhesion. Molten aluminum alloy is poured into the mold under gravity or low pressure. After solidification, the mold is opened and the wheel casting is removed. The casting then undergoes heat treatment, machining, and finishing. This method ensures consistent quality, good surface finish, and high structural integrity. The production of the all-new $100 US dollar note is a complex, multi-stage process designed to ensure durability, security, and accuracy. It begins with the creation of a special blend of cotton and linen paper, embedded with security threads and watermarks. This paper is then printed using offset and intaglio techniques. The offset printing applies subtle background colors, while intaglio printing adds the raised, tactile features including portraits and numerals. Security features, such as the 3D security ribbon and color-shifting ink, are integrated during printing to combat counterfeiting. After printing, sheets are inspected for defects using high-speed scanners. The sheets are then cut into individual notes, sorted, and packaged. The entire process is conducted under strict quality control at the Bureau of Engraving and Printing. Each step ensures that the final product is not only secure, but also consistent in appearance and performance. Big steel, big force, big precision. This is how artillery shell casings are forged, one massive step at a time. It begins with heated steel bars, up to 130 millimeters in diameter. A hydraulic press knife from Ficep cuts them down to size, each segment ready for battle. Next, the red-hot billets are moved to a 630-ton forging section. The EUMUCO forging machine hammers them into shape with a 1250 millimeter stroke. Once folded and formed, the steel bodies enter a second section, drawing and calibrating. Here, 200 tons of pressure and a 3,200 millimeter stroke refine the shape using rollers and rings. A programmable lathe takes over, rough-turning each casing to form. Then another lathe completes the final contour, every shell identical in size and symmetry. An automatic magazine loads new blanks for continuous production. Inductive heaters by EMA ramp up the temperature to forging conditions again, powered at 375 kilowatts, 1000 HC. At last, a vibration forging machine from Wecker delivers the final shrinking operation, tightening tolerances and strengthening the casing walls. From glowing steel rods to precision-formed shells, each step is sheer industrial choreography, brute force guided by automation. From Arctic rock to high-tech power, nickel travels farther than you think. At Canada's Raglan mine, nickel ore is blasted, crushed, and floated, raising concentration from 1% to 18%. The powder is shipped north to Deception Bay, braving sea ice to reach Quebec. From there, it's smelted in Sudbury at 1,380 degrees Celsius, reducing impurities and yielding matte with 60% nickel. Each link in the chain transforms raw geology into global utility. Final refining happens in Norway. Electroplating inside massive acid tanks produces 99.99% pure nickel, ready for batteries, steel, and aerospace. What's mind-blowing? Nickel is endlessly recyclable. From mining to reuse, the cycle never stops. A plain coil of aluminum feeds into the gutter machine, and the magic begins. Rollers shape the metal into a seamless channel, long, clean, and ready to install. Every curve forms with fluid precision, no joints, no leaks. Finally, the gutter exits the machine, custom cut to the house's exact length. That smooth transition, so satisfying to watch.